Okay, now the recording is started. I'm going to go ahead and get started. Welcome to the Ross Controls Fluid Power Safety Selection, Implementation, and Validation presentation. And with this, we are, as I said, I am recording this, that we will be able to reuse and post on the website at some point. We are also, if you have questions, please put those in the participant feedback box. I will answer those at the end of the presentation. And so if you want to hang on for answers for those questions, if not, you can email me directly. And with that said, we're going to go ahead and get started. And what I would like to do is kind of review some things we covered in session 1 and then get into safety system selection, just a very basic look at a machine, get into the safety implementation and design process, and then talk about something called safety system verification and validation. And to me, this is one of the areas that most people fail in their design process. And then we'll just talk about, what Ross can do to help and then have a few closing comments. So with that said, I'm going to go ahead and talk. You remember in session 1, we said that the laws don't really tell us what to do. They tell us that we need to do something. And, the two primary laws that are referenced all over the world, OSHA, of course, in the United States, Machinery Directive in Europe, but many countries are following something like OSHA or something like the Machinery Directive. For example, if you look in Korea, it's KOSHA. So it is Korean OSHA. You look at the GB standard in China, it is very much based on Machinery Directive. So there's a lot of similarities between these two standards because they do reference requirements. Those requirements are published in the standards. They are the standards are the technical specifications that tell professionals how to implement safety solutions to make their machines compliant. And we said there were 3 types of standards, and we said there were C-type standards for specific machines. And I'm going to use a machine today that has a little bit of everything, so there's not a direct C standard for it. So we will be applying A and B standards in determining the right risk reduction measures for this machine. And the areas we're going to look at is the outcome of the risk assessments. We're going to look at the design principles, and like I told you earlier, ANSI B1119 in the U.S. is directly referencing ISO 13849 and IEC 62061 as best practices. And then we're going to, factor in a little bit on pneumatics and hydraulics. And like we said, B110 and 26 both reference EN ISO 4413 and 4414 as best practices. So we're going to concentrate in those 3 areas in this portion of today's presentation. And I think you remember from session 1, we talked about, a lot of times people are using a basic assessment tool like ISO 13849. And in this example that I showed the other day in session 1 with the hydraulic press, it showed that that ISO methodology came out with a performance level D. And when we actually did pressure and force analysis, due to the catastrophic nature of the potential injury and the force that was applied, they really would have had designed to meet a PLE. So, as I said in that presentation, people are following a 3-step approach using a basic assessment method. And then if they identify that there is fluid power risk on the machine, they're doing additional pressure and force analysis to see if the performance level suggestion from the basic assessment was good enough or not. And then once they determined what that performance level needed to be, a lot of the companies are looking at what type of risk reduction measures do I need for that specific mode of operation. And we kind of have that broken into 3 areas, energy isolation or lockout tagout. That's typically for maintenance, service, and repairs. The normal operations is around your production activities. And we had said that 60 to 70% of most injuries happened in abnormal things that occurred during the process that wasn't part of maintenance and maybe not part of normal production, like removing a jam. A jam is not a normal thing. Maybe it's a changeover. Maybe it's an adjustment. it could even be cleaning. So we have to look at how we want to treat these abnormal modes of operation. And so we need to look at every job task and every mode of operation, and we also need to look at every energy source in order to have the best possible risk assessment. And so what I'm going to do is just kind of look at a very basic machine, and this is very common in the industry, where you might have a robotic weld cell. Yeah, there is an ANSI RIA standard for robotics, but if you look at the fixtures are more machine safety type, meaning they have pneumatic clamping systems on here. They have a motor that rotates the fixture. This is very common in the welding industry, where you may have multiple fixtures that are being welded by one robot. You may have multiple operators to take care of on the machine. And as this one has no guarding on it, I'm just going to look at a simple function like loading and unloading of parts. For time's sake, in an hour, we don't have time to do a full risk assessment. So just keep in mind, we're looking at one mode of operation only and two tasks, loading and unloading of the machine, okay? So with that said, I want to just kind of, show how these fixtures are made up. And you can see here on this, in the top left image, there's multiple clamps here that are holding tubing in place for a welding operation to occur. And in many times, these weld fixtures might be on two sides of a table. So in the bottom right, I have a rotary table here showing a very complex machine frame for an automobile, and this one has like 30-something clamps on it, and it's very long. So this might be a 10-foot long table, a 15-foot long table, 20-foot, or it might be 2x2. So, and there's varying levels of complexity depending on how many components are used. So we're going to look at a simple machine application, and we're going to assume that we had 663 newtons of force, and I'll show you why I'm using that, because I had used that on a weld cell for another customer, and so we're going to use it as an example. In this example, a person was loading the parts every 30 seconds, and then the clamps moved at a fairly slow speed of 200 millimeters per second, or 10 inches per second. And that is slower than the safe speed reference that we hear from the robot standard. The robot standard is where they have the best definition of safe rated speed or safe limited speed. And those of you who have robots probably know that when it's in program mode or in teach mode, it is limited to 250 millimeters per second, or 10 inches per second. It is in a slow mode, and that's where the safe speed reference comes from. In many cases, is from the robot standard. And so if we apply this and start looking at this in accordance with the basic ISO 13849 method, we said in session 1, S1 is a slight injury. That is something that could be treated with in-house first aid. S2 is anything more than that in-house first aid. If someone has to go out to get stitches, go to the doctor, the hospital, or even, to the morgue, it's a serious injury. There are other risk assessment methods that have 3 or 4 different severity levels, but this ISO method, as I said, is very basic, and it only has 2 levels. If I look at frequency, generally people are looking at, is this happening more than once per hour or less than once per hour? So people are using that F1 as that low, less than once per hour, and anything more than that, they're looking at this as being an F2 because it's every 30 seconds. There are standards that have 4 to 5 frequency ratings, and they look a little bit deeper. Is it I'm going to be exposed to the hazard one time for 10 minutes, or am I going to be exposed 50 times for 30 seconds? So they have different criteria selection, but this ISO method is very basic and only has 2 levels. And then that possibility of avoidance, the P1 and P2, since we are less than that 250 millimeter per second or 10 inches per second, we're going to say P1. That led us to a performance level D requirement from the risk assessment. Okay? Since this is got pneumatics we need to look and evaluate that force, okay? So an example would be I need to look at what the bore is of that cylinder. I need to look at what the tooling looks like on the end. Is that tooling flat, or does it have a sharp point that can pierce me, or has it got a very sharp edge that can cut me? We need to understand that tooling, the speed it moves at. We also need to understand what happens if I turn off the air and it drops. Now we have gravity to worry about as well. So we have to think about these things and look at what this potential injury could be. So in looking at this, when I was looking at it for a customer of ours, they were using incoming line pressure, which happened to be 100 regulated to 100 psi, and they were using standard control solenoids that they were driving their clamps with. So they had a person hitting the foot pedal while their hands were in the machine, and this thing was clamping. Well, here's where the problem comes in. When you take that 100 psi on a 3/4 inch bore cylinder and you have a flat clamp surface of a 1/2 inch by 1/2 inch or 12.5 millimeters by 12.5 millimeters, you're going to be right at your force is going to be right at 663 newtons. And if you remember, we had a chart the other day that showed that 663 newtons would be powerful enough to create a serious injury. And if I look at that serious injury says, oh, performance level D, because it's between 400 and 2,000 newtons. That's 663 newtons falls right in PLD. So even doing pressure and force analysis, we came up with the same thing as ISO, the basic ISO method here. So we have verified that it's PLD for both the standard hazards and also the fluid power hazards here. So we're going to take that PLD and roll with that. And you remember the standard for pneumatics is ISO 4414. And if you look at the bottom, section 5.12 says the control system shall be designed in accordance with the risk assessment. What that means is it's got to be designed to meet performance level D, because that's what the risk assessment said. And if this requirement is met, you meet the requirements of ISO 13849. So I'm going to show you that part now. We've done the assessment. Now we're going to get into selection, mitigation, and then verifying that our design and product selected meet the correct performance level. So we're going to jump into that now. And you remember in ISO 13849, it says pneumatics and hydraulics are part of the safety-related part of the control system, and it requires proven in use or well-tried. Of course, Ross's have been proven in use and are also well-tried. We have tested these, and we have tested them to a standard and have proven what our B10D value is, which is our failure rate, and we have proven what performance level our product can be used in, what type of systems. So with that said, we have to start thinking about when we pick products. A lot of times I see people picking a nice Category 4 rated light curtain, a nice Category 4 safety relay or controller, and then they put a standard valve out here with no feedback sensors or anything. And that valve might be a Cat 1. Well, when you start looking at this, your weakest link in the chain limits the potential that you can achieve as a system. So with a single Cat 1 valve with no monitoring, my system is limited to a Category 1. So in order to get to those higher levels, we would have to choose products that meet those requirements, or we maybe have to have redundant lower level products to get to that requirement. So the easiest way is to use recognized safety product like Ross's. And if you look at our RSE valve, it does safe exhaust. It also does safe return. And now we can do dual pressure select with it. So we're using this valve can meet Category 4. So if we have a Category 4 light curtain, a Category 4 controller or relay, and a Category 4 output device, we can say that our safety function could potentially meet the requirements of Cat 4. But now we got to look at the other pieces. And I'll show you this when we get to the ISO 13849 portion. It is made up of category plus something called reliability and another piece called diagnostic coverage, and a fourth piece called CCF, or common cause failures. So we have, if we start with a good quality product that is at a high level like these are, it gives us a better opportunity to meet the performance level requirements down the road, and I'll show you that now. And if you remember, we said that the Ross solutions fell into two areas: engineered safeguards, or what I would call administrative procedures. And if you look at the blue curve on the right, it has engineered safeguards there in the middle, and then you get down to administrative controls. The administrative controls is where you have these procedures for lockout, tagout. And so, you know, if you start looking at that hierarchy, that's where Ross's products primarily fall. And if we start looking at ISO 13849, you know, as our design standard, there is a published list of safety functions that's published in Table 8. And, you know, there are a number of functions. And just on this simple welder, let's look at what might be possible. You know, we talk about a safety-related stop function that's initiated by a safeguard. Well, think about this. All of us have seen machines. When I open the door, the machine stops. Or when I interrupt the light curtain, the machine stops. Or I hit the emergency stop button. It dumps energy and stops the machine. Well, those devices, that e-stop, that light curtain, that door switch, they are what is initiating the safety function or the safety-related stop. So that is a function. And if we think about when I hit that e-stop and air dumps, we have to restart the machine to resupply air. So maybe restart and restart could be applied on a solution on this machine. Another one might be, if you look at the fourth one down, energy isolation and dissipation function. Okay, well, I interrupt that light curtain, I dump air, or I hit that e-stop button. Another one might be parameterization of safety-related values. So what if I interrupt that light curtain and I suddenly change the speed of the robot, or potentially I reduce the air pressure supplied to the machine? These are using parameters to drive different safety behavior. And then, of course, there's always an e-stop function, because as we know, every machine needs to have an e-stop. So these are all functions that can combine to make a complete machine solution. But for this simple application where we're loading and unloading parts, maybe the best two might be energy isolation and dissipation function. That means I interrupt that light curtain, I dump my pneumatic energy. That way the clamps have no potential to cause harm. So we just dissipated the energy there. This is a energy isolation and dissipation function. The other one, using parameters based on monitoring of input devices. So maybe you know, reducing this to safe limited pressure might be an option. So we got a couple options here. So let's compare those two options, and let's look here at the safety selection flow chart. You remember we do have a a main flow chart that Ross has created to guide users towards solutions. And if safe exhaust is here, we have a series of questions that would lead you to an individual valve type or valve name. And then we have the same, something similar for the pneumatics, or I'm sorry, for the reduced pressure. And then, so we need to think about this and think about how these two valves would operate and what it means to our system. So we have to think about it in a systematic way. So what happens if I use the safe exhaust valve and it would dump every time a person loads or unloads parts? Yeah, it's probably the safest because there's no potential for energy. But what are the issues with it? Well, there's a significant functionality loss. For example, if that clamp is moving forward, when I interrupt the light curtain and I dump air, do I know that it finished its stroke? Do I know where it's at in the stroke? No, we don't, because it just coasts to a stop. So we have no idea where it's at. And then what you have to do is you have to go in and resupply air. And so there's a huge time loss between exhausting and resupplying air or repressurization. And then air is one of the most expensive utilities in the plant, and there's significant air loss. So that could be some issues. And one of our customers told us that, they're loading parts every 30 seconds, and they lose, 3 to 5 seconds every time they load parts because of dumping air and then resupplying air. Well, what we suggested to them was maybe using a pressure select valve. And with a pressure select valve, it allows us to set a high operating pressure and a low operating pressure. And what would happen with this function, every time someone interrupted that light curtain to load or unload, the air pressure would go from the high air pressure, and we said was 100 psi, to a lower pressure that could potentially meet the safe threshold. And we'll talk about that in a minute. But in doing this, if we were able to do this kind of activity, there's not a lot of functionality loss because you're still clamping, but at a lower pressure. And it's a minimal loss of air because you're not completely purging the fixture of air. You're just purging the difference between high pressure and low pressure. And you don't have a lot of lost time due to exhaust and repressurization. So in my opinion, probably the safe pressure select, if we can get to the right pressure level, would be the best. So let's look at that and how we would do that. We would typically make an assembly that would have a lockout valve on the left because, all machines need lockouts to do service and repair and maintenance activities. You would probably have a filter to make sure there's no debris that gets into the valve. And then you would have pressure regulators, 2 of them in parallel, a low pressure regulator and a high pressure regulator. If those are lockable, which Ross does have a set of lockable regulators, you could lock these at a given 2 different given pressures, supply that to the RSE valve, and then the RSE would select between the 2, depending if the light curtain was interrupted or not, and would send the appropriate pressure out to the standard solenoid bank, which is driving the clamps. So with this particular customer, we looked at what if we were able to go at a lower pressure, maybe like 33 psi, with that same 3/4 inch bore cylinder with a 1/2 inch square clamp surface. It reduced us to 140 newtons. And if you remember me showing you the other day, that 150 newtons has become the generally applied limit that is used for safe, what they call safe limited pressure. And so doing this calculation, we're proving we're getting there. And if we look at what ISO 13849 says, it says that a method of elimination is substitution or limiting interaction. So if we automated the process, we, of course, eliminated the potential injury, but you can also do substitution, which is reduced energy. And it says, lower RPMs, lower force, lower amperage, lower pressure, lower temperature. Well, if we have gone to a safe limited pressure, we have done elimination through substitution. And we are driving that with a safety-related part of the control system. So we are using a safety light curtain to send a signal to a safety controller. That safety controller is then controlling our dual pressure select valve and selecting the correct pressure, and we're monitoring the sensors on the valve to make sure that action occurred. And in doing that, we are meeting the safe limited force and power requirements from Table 8 of ISO 13849, or if you're looking at B1126 or VDMA, they call it safe limited torque or force. So if we have reduced the pressure, we have limited the torque. Okay, so that is how we're justifying using this, because we are getting below that 150 Newton threshold. So if we have done that, now we got to start thinking about how to pick the individual product. If I got to the RSE valve, and if you look at this table, we got safe pressure select, and it's got a yellow tab, and that would be on the would lead you to the RSE page. Once you're at the RSE, you could go to rosscontrols.com, and you could go in and when you click on that, it brings up the home page, and it does say that Ross Controls is the global leader in fluid power safety, because we do more than just pneumatics. We also do hydraulics, and we also do advanced lockout and process safety as well. And if you clicked on the industry and applications page, the first drop down in that menu is safety. If you clicked on that safety tab and scrolled down on that safety page, there is the safety valve selection tool. You could go in and click pneumatics. Since we are doing pneumatics, click on the valve type that you want. And what it does is it brings up a list of questions like what port sizes do you need, how much flow do you need, what voltage, you know, that kind of stuff. And it would limit you from the 6 products that are possible to 1. Once you've gotten to that 1 product, then you can click on View Product, and it brings up the price plus the estimated ship date. And what this is, it is our online store, and you can buy at list price plus 3%. Or you can go to our distributors, and we have our distributors also listed on our website. And our distributors, you know, get a bigger discount than that, so they can probably get you a pretty good price. And then we also have the integration guides. And if you look at the tab here on the right, if you scroll down from where you see the price and part number, it would have these at the bottom. So it's got the product information, it's got the operating instructions, and it's got the integration guide. The reason I'm showing you these, because we'll use these in just a little bit. If we go ahead and scroll on down and start thinking about, now we have picked the safeguarding solution. If we pick the safeguarding solution, it's got to be designed and constructed to meet a standard. And I think you remember from session 1, we talked about EN 954 is where categories came from. EN 954 was withdrawn in December of 2011. When something is withdrawn means it can no longer legally be referenced. The only place categories exist today is as a subpart of ISO 13849. There is another standard called IEC 62061, and it is both ISO 13849 and IEC 62061 are called functional safety standards because they both look at how well the safety system needs to function. Well, which standard is right? Well, for us, it would be ISO 13849 because IEC 62061 is what they call for EEPE. What that means, electrical, electronic, and programmable electronic systems. And it does not really give any guidance on pneumatics and hydraulics. And as a matter of fact, it says if you have hydraulics and pneumatics, see ISO 13849 for guidance. So if we do have a fluid power hazards on our machine, all apparent standards point to ISO 13849. Even in the U.S., NCB 1119 will point you to ISO 13849 as the best practice. So with that said, we are going to look at what this says. You've heard me mention that categories no longer legally exist. The only place they exist is as part of a performance level. Well, people ask me, what is a performance level? Well, it's basically a category on steroids. Okay, I'll explain that in just a minute. It is an improved category. So if we look at what made up categories, it was basically a circuit, and that circuit is either single channel or dual channel. Single channel is not fault tolerant. A dual channel is fault tolerant. So it's got a structure piece to it. It also has some diagnostics. But category, as I said, was withdrawn. And there was from category B to category 4 is what we had. Now, I want to show you why that standard was withdrawn. It was because ISO or EN 954 was a basic standard that was developed in the 1990s and published in the 1990s, and it was for basic electromechanical components like contactors, like switches, like door switches, things like that, safety relays potentially, electromechanical devices. Even valves are considered an electromechanical device. Well, guess what? In the late 90s, you started seeing light curtains. Well, guess what? They're solid state. So EN 954 did not address solid state devices. So that's why ISO 13849 and 62061 came into play. Both of those were developed for more advanced solid-state type products. The issue is that 62061 did not include fluid power. ISO 13849 did. So that's kind of where we're at. So with that said, I want to look at what the big differences are. From categories, you had just this basic structure that supplied your diagnostics and your fault tolerance. Well, you still have that. There's still categories existing as part of performance levels, but what's been added is reliability. So it's looking at the reliability of the components. It's looking at the systematic approach of design and implementation. It looks at something called SRS, Safety Requirement Spec. What are the safety requirements for the system? And then it looks at something called functional safety management. How are you managing that design process? So it basically adds a whole lot of levels of basically looking at diagnostics, reliability, systematic design approach, and it looks at the safety requirements that are needed. So with that said, I want to jump on into how we apply these. ISO 13849 has two parts. Part one is safety-related parts and control systems, and it covers the general principles for design. And part two, again, is safety-related parts and control system, but it deals with validation. So we're going to dig into both of those in the next few slides. And if you look in ISO 13849, it's got a figure 1 here on the left, and it looks exactly like ISO 12100 because it is a screenshot of that. And it's got the same steps: determine the limits, identify risk, estimate the risk, evaluate the risk. And then at the bottom half of that, it's reduce the risk. So if we're going to reduce the risk, we need to follow a process. That's where figure 3 on the right-hand side of the page comes in. I'm going to dig into figure 3 in the next few slides, but it gives us a systematic risk reduction approach, okay? So once we have done the risk assessment, we need to identify the safety functions. So what did we just identify a few minutes ago? We identified a safety function for loading and unloading. So we identified an input light curtain, a safety relay or controller, and a safety valve. So we have identified the safety function we want. So we've identified the characteristics of that safety function, how we want it to operate. And we identified the required performance level through our risk assessment. That's where the term PLR comes from, the required performance level. And then we identified the safety-related parts of the control system for each of those functions. Now we need to evaluate it, and that's where we get into this, what I call design verification piece, okay? And then once we get in this design verification, we need to verify that each safety function that we identify meets the requirements of the risk assessment, meaning did we meet PLD with our system? So I'm going to look at this aspect next. So what we've done so far is we did a risk assessment. We identified the required performance level. We identified the safety function, light curtain, controller, and valve. And we identified the pieces that we want to use. And then we also identified the characteristics of how we wanted this thing to operate. As we said, we want to switch from low pressure to high pressure when we interrupt the light curtain. When we come back out of the light curtain, we want to go from low pressure to high pressure. Okay, so we've identified our functionality. Now what we're going to do is we're going to jump into the design piece. So we've done these first 4 steps. Now we need to get into the last 2, okay? And keep in mind, we did this for one task, and that's loading and unloading. We did not do it for all other things like cleaning, adjustment, changeover, things like that. We have to look at every mode. So a machine solution is typically made up of multiple safety functions. Okay, we're just doing one. Keep that in mind. So if we think about a safety function, safety functions are made up of, we said, input, logic, and output devices. And we have to look at how we're going to structure these systems, meaning what category are we going to use? Single channel, category B, 1 or 2, Or are we going to use a category 3 or 4 dual channel? So we need to determine our structure. And then we need to take into account what is the reliability of each of these components. And that would give us what we call MTTFD, mean time to dangerous failure of the system. There's calculations here. Okay, another piece is diagnostic coverage. That is the ability to monitor dangerous faults in the system. And then another one, especially if we're using dual channel systems, is what is a common cause failure? So what kind of failure can make multiple components fail at exactly the same time? So common cause failure. So we're going to look at these 4 attributes of the performance level in the next few slides. As we said, categories is the biggest piece of a performance level. And so we're going to look at those categories now. A Cat B and Cat 1 system, as we said, is a single channel, and there is no safety logic in those type solutions at all. Once you get into Category 2, this is where you have safety monitoring logic. It is still single channel. It means that my light curtain is sending me one input to my safety relay. My safety relay then is sending me a single output to a single valve. That valve then is giving me feedback on the status of the valve. It's single channel, but it is being monitored by a logic device, and it is doing testing and evaluation. Problem with that, one failure leads to the loss of safety control. So if that input device shorted in an on state, you would never be cycling your outputs because it's always given a positive state to your logic device. That's why most multinational companies that I know have selected a minimum of a Category 3 and a lot of times Category 4 dual channel system. The big difference between Cat 3 and Cat 4, Cat 3 is monitoring on demand. That means when I place a demand on the safety function, I look at the status. Cat 4 means I'm constantly monitoring status, and it has a higher diagnostic coverage, okay? So we'll look at these categories. And if you look at a system and you see standard components out here, you're most likely going to be at a Category B, maybe Category 1. Category 1 typically does not have a logic device. A lot of Category 1 systems that I see are using mechanical switches with direct-driven contacts. So there is a symbol of an arrow that is on the front of a mechanical door switch. Same thing on a pull cord, same thing on an e-stop button. They are physically driven closed, and they are physically driven open by mechanical means. And the way these are made is the conducting bar on the contacts will break if they weld, and it's always going to fail to a safe state. So most Category 1 circuits do not have a monitoring device, but they will fail to a safe state on the input side, and it will absolutely remove power to the contactor or the solenoid. You get into Cat 2, this is where we start seeing safety devices being used, like our PO checks are Cat 2. So you start looking at Cat 2 devices. You've got Cat 2 circuit. You've got a single channel input device going to a safety logic device that is sending a single output that's to a safety product that has diagnostic feedback. This is a very typical Cat 2 circuit. It's a good, reliable circuit, but a single failure can lead to the loss of control. When we get into Cat 3 and 4, as I said, is when you see dual channel systems. And with these dual channel systems, typically you've got 2-channel input, you've got a safety logic device, whether it's a safety relay, controller, or PLC, that's driving redundant outputs with feedback. So if you think about a valve, basically a Ross valve, most of those are redundant valves with diagnostic feedback to the system to tell, hey, I've got a problem if one of these elements sticks. And so this is a very typical Cat 3 or 4 circuit from electrical aspect. And with a valve, you just replace those 2 contactors with a double acting valve or a double spool valve, what we call a dual safety valve. The next piece we have to look at is reliability of the hardware. And what you see a lot of times with electrical devices, you will either see a PFHD or an MTTFD. basically what this is a failure rate. And it is a failure rate to when, or it's a failure rate of dangerous failure. On electromechanical devices like a contactor or a valve, you're going to see a term called B10D. This is when 10% of the products being tested fail to a dangerous state. And this is B10D is for electromechanical components, okay? So you have for solid state and electronic components, you'll have MTTFD or PFHD. For electromechanical, it's going to be B10D. Well, when you start looking at solid state devices, you will see a mix. So you see 15 times 10 to the minus 9. Well, that is a PFHD. That is a probability of dangerous failure per hour. So if we take so we would have to understand our number of operations, and we'd have to divide our number of operations for our machines, which if we're cycling every 30 seconds, it would be 691,200 cycles per year. And we would divide that into that 15 times 10 to the minus 9, and that would give us a MTTFD value of 217 years. Now, many manufacturers will list theirs. They will have an MTTFD, but what they've done is they have taken some assumptions whenever they do an MTTFD calculation. A lot of times you will see PFHD, but sometimes you do see MTTFD. On a device like Ross's with a B10D of 20 million, what you have to do is you have to determine your number of operations of your machine, and then you have to divide your B10D by the number of operations times 0.1. And I'm going to show you that in just a second. But there's also a default table in ISO 13849, Table C, and Table C has default values. So like if you look over here, hydraulic components, and if you go across, that's the second one in the list. If you go across, it gives you an MTTFD of 150. Well, let's go on down to maybe, let's say, a pneumatic component, and you see a B10D of 20 million over here. There are some default tables that are used. Again, that is not as accurate as having data from the manufacturer. So what I'm going to do is show you a little bit more how we would use manufacturer data. So, for example, if I had my machine and I knew that the B10D value of my valve, which the Ross RSE valve is rated at 20 million, so I'd have 20 million, and let's say our machine is operating 360 working days per year, 16 working hours per day, and a time cycle of 30 seconds or every half minute. Our number of operations per year would be 691,200. What I would do would be divide 20 million, which is our B10D. I'd divide that by 0.1 times 691,000 would give me a value of 289 years, would be my MTTFD value. Well, what you would do then is you would look at what your MTTFD is of each of your devices, and you would come out with the MTTFD average. Since our relay was 300 and some years, our light curtains were 200 plus years, and our safety valve was 289 years, we are going to more than exceed the high level, which caps out at 100 years. So what we would say is we have high reliability components. If we did our evaluation and we came back with a value that was between 3 and 10 years, that would be low. So what you have to be very careful of on high cycle applications, you may end up with low MTTFDs depending on what the rating of the product is. But basically, this is a prediction of failure and reliability of the system. And so we're trying to shoot for the highest MTTFD we can get. So with our system, we're going to be in the 200 plus, which puts us in a high diagnostic average. So we have a strong category. We said we wanted to do a dual channel, Cat 3 or Cat 4. we said that we have high reliability. Now we need to look at diagnostics. And if we are looking at what we call indirect monitoring, this is where we have monitoring by a pressure switch. It's 0 to 99%. But if we look at something like a control valve and we're doing direct monitoring in the valve, well, that gets us 99% diagnostic coverage. And so with most of our valves, we say we have a 99% because they are monitored directly as part of the valve. If it is external from the valve, it depends how far your monitoring is away from the valve. A lot of people, for example, don't check their valve, they check the end effector, like the cylinder. Well, that would be indirect monitoring, where we're getting more direct monitoring right off of our valves. So we can say 99% with the Ross valves. So what we have to do then is we need to understand our diagnostic coverage. So what we're looking at is we are taking the failure rate of all detected dangerous failures, and we're dividing that by all dangerous failures in order to get diagnostic coverage. We're shooting for higher the higher the diagnostic coverage, the more reliable and better capability to detect faults we are. So with that, what we have to do is take those MTTFDs that we calculated and the diagnostic coverage for each device in order to determine the diagnostic average. So we would have a diagnostic coverage of our input device, light curtain, divided by the MTTFD of that light curtain, which we said was 217 years. And so, and we would do this calculation you see right here. It's quite burdensome, but that gives us diagnostic average. And as I showed you on the previous chart, if we're ending up with diagnostic averages that are medium to high, that's getting us up very well in the ability to monitor faults. Well, I'm going to show you how all this ties together in just a second. And let's say, and I just put some assumptions in here, let's say we only had 60% diagnostic coverage on the light curtain, which I know we don't because they have 99%. I'm just showing you as an example. And let's say we had 40 years. I wanted to show you some differences. So that, and let's say the logic device had 90% and 70 years, and our Ross valve had 99 and based on number of operations, 269 years on MTTFD. We know we're much higher with the components we selected, but this is showing 73. If we did the calculation on our system with the components we selected, we're going to end up in the 99% diagnostic coverage area. We're going to be in the very high area. But the reason I'm showing you that is there's also a score for diagnostic coverage. So we have a structure, we have a component reliability in terms of MTTFD, and we also have a diagnostic coverage piece. The next thing is common cause failures. And what we're looking at when we have a two-channel system, we're looking at what causes both systems to fail. Like what kind of external stress could cause that, like temperature, dirt, it could be shock, it could be water. If it's a non-washdown product, it gets wet. What can cause these things to fail? And that's what we're looking at with CCF. So CCF uses a table, and you get a score. And based on what you're using and how you're applying your system and how you're designing your system, you end up with a CCF score. And the target is to end up with more than 65. And so it looks at, okay, am I separating my wires so that I don't have potential shorts, for example? Another thing, am I, for example, running my 24 volts separate from my AC voltage so I don't get noise put on the 24-volt circuit to cause problems? It's just good engineering practices. And, you know, so when we design our system, we're shooting for that 65. So what we do then, we knew what our performance level required was. It came from the risk assessment. Now we need to do the validation. We did these calculations. Let's look, how did we end up? So you remember I said we had more than 100 years reliability. That gave us high reliability. And then we used a Category 3 structure. So if we look at the bottom here is the category. If we used a Cat 3 structure, and we use components that are highly reliable. That's what's shown here. And, you know, I showed you 73 in the example of diagnostic coverage. At 73 low, we still met our performance level D here. But you remember I told you we were actually at a high level. So if we are high at high reliability components, you know, we're up here. So category 3 plus high, we're gonna end up in, you know, Cat 3, Cat 4 system. So we're more, or I'm sorry, a PLD system. So we're going to be at a PLD or a PLE. We're going to more than achieve what we were targeting. Okay, so that is basically your design verification. And you just did a design verification calculation, and you validated that your performance level met PLD or higher. So I showed you how to calculate it, but there are tools out here, something called Systema, and Systema is a calculator tool that was written by the IFA in Germany. And basically what it can do, it can drive you through and do these calculations for you. So the user would need to populate the MTTFD values of the products, the diagnostic coverage, the structure, and CCF. They would have to populate that, and it would calculate it. There is an option. On the Ross website, we do, on the safety portion, we have a link to the safety integrity software tool for the evaluation of machinery, Systema. You can get it and load it right there. You can also, if you click on the Get Started tab, you can download Systema, and you can download our product library. Most of your well-known safety companies have libraries for their products, so you don't have to input a lot of data. You just go and click on, I'm using a Ross DM2C, or I'm using a Ross M35, or the RSE in our case here. Click on that RSE, it populates the data for you. So what this tool does is it does all of these calculations we were talking about back here, and there's the library tab at the top. You can click on it and bring our product in, product data in. And what it does is it comes up and it does the performance level calculation for you and says, oh, you were trying to meet PLD? Well, you actually achieved PLE. So it will do the calculations for you. In other cases, we've had customers say, help us develop a guidebook on how to do this. And so for a lot of companies, we're helping them understand how to implement our valves into safety circuits to get the right level of diagnostic coverage, to get the right reliability of the system in order to meet the performance level they're trying to achieve. So we work with a lot of companies in doing this and can help you and your customers and your engineers with a guidebook like this if you're interested. So that is one piece. Now we have created integration guides to help with that wiring, with those schematics, with the code, and also with validation plans. And you remember me saying earlier, people are designing and implementing solutions, but validation is the part they're missing. And so one of the last steps when you are starting up and commissioning your safety system is you have to do validation and verification. A lot of people call it V&V. What has to be validated is I have to validate my wiring and make sure it has been wired right. So there's verification and validation of wiring. All right, did it operate as I intended it to operate? So you're looking at design verification and validation. There's another one. If you've got a safety system that's networked, a lot of times your control system with a robot, for example, will be networked. So you have to verify and validate that your network's working properly. And guess what? If you're using controllers, you have to verify and validate that your control programs are correct. So there's a lot of validation that has to be done. Well, guess what? Both ANSI and ISO 13849 say verification and validation's got to be done. Now, let me show you a couple of things here. Testing and verification of the operation of the safety devices and their circuits. And look here, that testing should also have looking at the possibility of defeat. So what this means is you should also be doing fault injection. What happens if I lift on a dual channel system? What happens if I lift the A channel wire? Did the system stop? What happens if I short channel 1 to channel 2? So there should be verification and validation, which includes fault injection. And so what it says is that validation can include that the circuit was designed and implemented correctly, that the wiring was checked after the installation and before commissioning, and the functionality was verified by the integrator, and that the safety devices were functioned and tested. It gets into it. What happens with these is that we need to have a documented process. So what Ross has done for every one of our products, we have a full verification and validation checklist that helps users understand, okay, what happens when I pull the wire off solenoid A, or when I pull the sensor wire off spool A. So we have what are the steps we need to do to validate that our valve's working properly. So verification and validation is, to me, one of the most critical parts that's most overlooked in safety system design. And Ross can help with that. And so Ross has published just recently a machine safety development process, and it kind of outlines the steps. You might hear from companies like Rockwell and Pills and Omron and different companies, safety life cycle approaches or safety development process. So that's what we've done here. Step 1 is that risk assessment that it should be done for all task and hazard pairs. There should be pressure and force analysis, and this would lead to the required system performance. Then you need to get into functional specification development. You need to determine the job task for each hazard, understand the functionality needs for those, determine the mitigation technique, and determine the required safety functions. Then you got to select that product, both the input logic, output devices. Then you get into the design and these design verification calculations that I showed you today. And then we need to verify that our design meets the requirements of the risk assessment. So we said PLD. Did we meet PLD? So we need to verify that we met the risk assessment requirement, which is what we did today. There also has to be installation and validation once the system has been during the commissioning phase of the process. There should also be periodic maintenance and testing of the safety system. A lot of companies do this in different ways. One of our customers that makes automobiles here in Kentucky, they have a pre-start every day before production, a checklist that they go through. I've got another company that's in the food industry. They do that on a monthly basis. I've got another company that does it biannually. But there should be periodic testing. And best recommendation, you should follow the manufacturer requirements for those particular products. So we will be covering this in detail in our new machinery safety guidebook that we're working on now and hope to have published in the near future. And with that said, we are at the end of the day's presentation, and I was just a minute over, so my apologies. And what I will do, if you want to hang on, those of you who didn't have questions can go ahead and drop off. The others that did, I'm going to stop the mute, and then I will start answering those questions from the chat box. Everyone have a safe and healthy holiday weekend. Take care.